Hello and welcome to the continuing videos for Math 1500 Calculus 1. So in this video, we're going to start developing rules for the derivatives of certain types of functions. So we've already seen the definition of the derivative. So now we're going to see how to use that definition to create some general formulas for functions that we can just start to use those rules every time instead of always needing to revert back to the definition of the derivative. You should keep in mind though, and this is very important, that you do need to know how to use the definition of the derivative because it's possible that you might be asked to use the definition to show a derivative, in which case you'll likely receive no credit if you actually just use the formulas. All right, so now we're going to be talking about these, creating these formulas, and so we're going to start with a few general rules about derivatives before we take a look at polynomials as a whole. So the first three theorems that we're going to use, and we'll talk about why they're true, are the following. So the first theorem is that if f of x is a constant function c, then the derivative of that function is 0. Geometrically, this makes sense because a constant function is just a straight horizontal line, the slope of which is 0 at every point. That being said, we're going to see why it's true using our definition. And so, for a proof of this, we're going to use our definition. So f prime of x, that's the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And so our rules for our function is we're going to take everywhere we had an x in here, we're going to replace it by x plus h in a bracket. However, there is no x here, so there's nothing to replace. In other words, the limit as h approaches 0 of f of x plus h is just c. F of x is just c, all divided by h. So that's doing a little bit of simplifying. That's just 0 over h, which is 0, which is equal to 0. So using our definition of the derivative, we can prove that the derivative of any constant is 0. All right, so let's take a look at our second theorem. So our second theorem deals with constant multiples. So once again, c is going to be a constant, and this rule says that if f of x is equal to a constant multiple of another function, then the derivative of f of x is equal to a constant multiple of the derivative of g of x. So we're going to prove this in a very similar way. We're going to start with our definition of the derivative using this function. Not only this function, but just, again, a lot of this has to do with notation and understanding what changes in the function. So in terms of a proof, so once again, f prime of x is equal to our limit as h approaches 0 of f of x plus h minus g of x, minus f of x, all divided by h. Straight up definition of the derivative. Now, anywhere there was an x, we're going to replace it with x plus h. In other words, this is the limit as h approaches 0 of c times g of x plus h. That's replacing every single x here with x plus h inside a bracket. Minus the f of x, which was c times g of x. And then, if we're taking a look at the constant multiple here, we notice that that can be factored out. So that leaves us with c times the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. Lastly, we notice that what we're left with here looks like a definition of the derivative. In fact, it absolutely is the definition of the derivative. But it's the definition of the derivative of the g function, not the f function. In other words, this is equal to c times the derivative of g, which is exactly what we wanted. So in terms of what this theorem tells us is if we have a function that we know its derivative, we can multiply that function by a constant, and that just means we multiply the derivative by the same constant. So that's going to be our second rule, or second theorem. And the third theorem that we're going to see in this section is as follows. So the third rule is actually a combination of two rules, one for addition, one for subtraction. The idea behind this rule is if we want to add or subtract the functions together and then take the derivative, then it's the same thing as taking the individual derivatives and either adding them and subtracting them. So you can either add them first and then take the derivative, or take the derivatives first and then add them together. But before we get to why this one's true, let's be clear of what we're not saying is true. So note, f times g of x is not necessarily equal to f prime of x and g prime of x. So before we start thinking that this is just some notation thing, it really is that if you're adding or subtracting the function, then derivatives work nicely. But if you're multiplying or dividing the functions, then they don't work nicely. When it comes to multiplication and division, we are going to develop rules for these as well in future videos. However, it isn't just the product of the derivatives, which is a very, very common mistake amongst students. So let's talk about exactly why this theorem is true. So once again, now for simplicity's sake, even though this is not a necessary step, we can just let h of x be equal to f of x plus g of x. So we're going to do the addition one. Subtraction is pretty much identical. You can see exactly where the plus is changed to minus, and I encourage you to write that one out for yourself. So we want to show that h prime of x is equal to f prime of x plus g prime of x. And we're going to see some similarities with the constant multiple rule. So h prime of x, that's equal to the limit as h approaches 0. Probably a poor choice of letter considering they're really standing for different things, of h of x plus h minus h of x, all divided by h. So that's going to be equal to the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x minus g of x, or plus g of x, all divided by h. So that's just writing the definition of the derivative and what that function's equal to. So every place we had an x, we're replacing it with an x plus h inside the bracket. Now we're just going to rearrange this a little bit. So this one's going to involve a little bit more steps and a careful use of a limit law. We're just going to rearrange this. We want to say that that's equal to the derivative of f, which is f of x plus h minus f of x, all divided by h. So we're going to put those things together. So we're going to get f of x plus h minus f of x, all divided by h, plus, and then our g of x plus h minus g of x. So g of x plus h minus g of x, all divided by h. All right, so we have just some simple algebra working with fractions, the fact that we can split this up into two fractions, and also combining the f's and the g's together. So since f and g are differentiable, that was part of our theorem, since they're differentiable, the limits exist. Which means, using our limit laws, we're allowed to split this up into one limit plus another limit. But that was one of our limit laws that only works if we're dealing with functions whose limits exist. So this is equal to our limit as h approaches 0 of f of x plus h minus f of x all over h, plus the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. But this relies on the fact that these limits exist because we're using the limit laws that you would have seen in the limit laws video. So that's f prime of x plus g prime of x, not g7 of x, but g prime of x. And there we go. So for now, these are going to be our first three rules. And as it turns out, we can combine these rules together with things about powers of x in order to get any polynomial. So what does this mean? So this means that to find, let's say, f prime of x, let's say we write out any polynomial. So let's say we have a plus bx plus cx squared plus dx cubed and so on. Eventually it would stop at some letter, let's say z, that's a bad choice, but x to the n. Let's say if we had some polynomial, if we can take the derivative of, let's say, x, x squared, and so on, well, if you know the derivative of x, then you can get the derivative of b times x. That's the constant multiple rule. The derivative of c times x squared, that's the constant multiple rule. d times x cubed, that's the constant multiple rule. A is the constant rule that we just saw, and a combination of the addition rule, and if some of them are subtracted, that's okay too. So now all we need is the derivatives of all of this, then we can find f prime of x. So we're one step away. How to find the derivative of any positive integer power of x. So what about the derivative? So remember, this is just another notation for that. The derivative of x to the n. So let's go back to some of the stuff we talked about when we were doing the x cubed example in the derivative as a function video. So that's going to be equal to the limit as h approaches 0 of x plus h to the n minus x of n to the n, all divided by h. The tricky term, of course, in this would be this x plus h to the n. So let's talk about it. So that's going to be x plus h times x plus h, so on, n times. So there's n of these things. So that's going to be equal to x squared plus 2xh plus h squared. So that's going to be two of them. If we multiply by a third, we saw before that that gave us x cubed plus 3xh, x squared h, plus 3xh squared plus h cubed, and multiplied by some more terms. So what happens when we do a fourth one? So we're going to get x to the 4. That's x cubed times this x. Then x cubed is going to get multiplied by h. And so we're going to get plus x cubed times h. But we also need 3x squared times x, which is 3x cubed times h. And here's where we're going to simplify at least what we're writing. So we're going to get, the rest of them are going to be terms with h squared or higher. Again, we may need some more of these things. But the idea is that when we take x plus h to the power of 4, we're going to get x to the 4 plus 4x cubed times h, plus some other stuff. And this here is going to be our x plus h to the 4. Maybe some other terms if it was higher than that. What about x plus h to the 5? So x plus h to the 5, that's going to be x plus h to the 4 multiplied by another x plus h. The idea here is we're trying to establish a pattern. So this is 4x to the cubed h plus the other stuff. The other stuff is going to have an h squared term or higher. So again, the other are the h squareds, the h cubes, and so on. We're going to see later, as with the derivative video when we discussed it before, that these terms don't matter very much. So once again, x to the 4 times x, that's going to be x to the 5. X to the 4 times 8 is x to the 4 times h. 4x cubed times x is going to be 4x to the power of 4 times h, plus, again, 4x cubed h times h, so that's 4x cubed h squared, again, plus some other terms. Those other terms are still going to have h squared h cubed, maybe even higher terms because of the h. So we're going to get x to the 5 plus 5x to the 4h. As for this term here, well, it has an h squared in it. So again, that can just be wrapped up into other terms. So again, the other terms are the terms with h squared, h cubed. These are the only terms that either don't have an h or just have one h. All the other terms have at least h squared. All right, and so we can notice that in general, if you believe this pattern, that x plus h to the n is equal to x to the n plus n times x to the n minus 1h plus, again, terms with h squared or higher. Now it is possible, it's beyond what we need it for, but it is possible to explicitly write out what all these terms are going to be. That's something that can actually be computed. In fact, so just as a side note, we won't need to use this, but the h to the k term would be n, if you know what factorial is, all divided by the k factorial and minus k factorial. If you don't know what the factorial is, feel free to read up on it on your own or ignore it. x to the n minus k, h to the k. We're not going to need to use this, but we could, and write out the explicit term for h squared, h cubed, like we did with the h term being nx to the n minus 1 and the x to the n term. We could do it with all the other ones, we just don't need to for this particular question. All right, anyway, so back to what is the derivative. So our f prime of x is the limit as h approaches 0 of x plus h to the n minus x to the n, all divided by h. So now that we have a somewhat formula for the x plus h to the n, we get x to the n plus n x to the n minus 1h plus h squared or higher terms minus x to the n, all divided by our h. So subtracting cancels off the x to the n's. That leaves us with nx to the n minus 1 times h plus the h squared or higher terms, all divided by h. So what happens when we divide by h? Well, in this term here, the h's are just going to cancel, leaving us with n times x to the n minus 1. In these terms, one of the h's are going to cancel, but since every single term there had at least h squared, that means that every single term has at least a factor of h remaining. So every term in this super bracket has a factor of h left over. Maybe many factors of h, but at least one. So what happens when we plug in h is equal to 0? Well, all of these terms are all going to be multiplied by 0. In other words, we get that this is equal to n times x to the n minus 1 plus a lot of zeros. In other words, that's n times x to the n minus 1. So theorem, if n is a constant, then the derivative of x to the n is equal to n times x to the n minus 1. All right, so this gives us a rule. Now, technically, we've only really proven it for n being a positive integer. That being said, this is a rule that works for every constant n. But it is important that n is a constant. This is not saying that the derivative of x to the x, which is a function, is not equal to x times x to the x minus 1. It's very important that what's inside here is a constant, not a variable. If it's a variable, this rule doesn't work. All right, so this gives us the ability to find the derivative of any polynomial. And in fact, it gives us the ability to do even a little bit better than polynomials if we're talking about constants n, which are not positive integers. So let's see a couple examples. So let's find the derivative, f prime of x, if f of x is equal to x to the 2018, if f of x is equal to the cube root of x, and if f of x is equal to 3x to the 4 plus 5x cubed plus 7 pi. All right, so all of these are just going to be taking advantage of the rules we've seen so far. A and C are both polynomials. B is not a polynomial, but it can still fall under this power rule coming from a positive constant for an exponent. So let's find our solution. So for a, we're taking the derivative of x to the 2018. So our constant multiple rule says that this exponent goes here, and then we take x and we subtract 1 from the exponent. So that's 2018 x to the 2017. Fairly straightforward for a derivative. For b, here we have to be a little bit more careful, and here's where it is incredibly important that you understand and know the way of going from a radical to an exponent. So this is equal to the derivative of x to the power of 1/3. But it's important that you know how to go from a radical to a fractional exponent. If you want to use this power rule, you need to be able to go from one to the other quickly and correctly. Otherwise, you're going to be getting wrong answers. However, once you've done it, it's fairly easy. You go 1/3, x to the power of 1/3 minus 1, which means you just need to subtract a fraction and get negative 2/3. All right. As for part C, again, usually we don't need to do it in quite as much detail, but for a first example, we're going to go through every single step. So our function was 3x to the 4 plus 5x cubed plus 7 pi. So we're going to follow our rules. Our first rule is our sum rule that says we can split these up into 3 separate derivatives. This is as much realizing why those rules are important as doing this specific question. The second rule says we have our constant multiple rule. Now that only matters for the first two, but we can factor out that constant multiple. And now everything else is just a power or a constant. So x to the 4, our power rule says that's 4x cubed. X cubed, our power rule says that's 3x squared. And this one here, as tempting as it might be to say so, that's not falling under our power rule. Our variable is x. Pi is a constant, not a variable. So this doesn't fall under the power rule, this falls under the constant rule. The constant rule says the derivative of any constant is 0. And so we get 12x cubed plus 15x squared. Now this looks like a 4-step question, but really, chances are once you get comfortable with this, you can probably get to the answer right away. The 4 times the 3 is 12, subtract 1, you get your 12x cubed, for example. And you may not need to explicitly write out every single step along the way. All right, so this is how we can handle any polynomial and some radical functions too, as long as they're not that complicated. So let's see one more example which doesn't really look the same. So in this example, we're going to find the third derivative if f of x is equal to x cubed plus root x plus 1 all divided by x squared. All right. So we have our function here, we want to use it, but all of a sudden we have division. And if you go back to what we said way back here, it was very clear we cannot take the derivative of the numerator and the derivative of the denominator. That is straight up not allowed. We will have a rule for that later, but that's later. We don't have that rule now. So if we can't just say it's the derivative of the top divided by the derivative of the bottom, what can we do? So we need to be able to write this function as something that's just a sum, a difference, a power, or a constant multiple. Which means we're going to rewrite this function as x cubed over x, which is x, plus x to the square root, or square root of x, which is x to the 1/2 over x squared, plus 1 over x squared. In other words, this is going to be x plus x to the negative 3/2 plus x to the negative 2. So we've taken something which doesn't immediately look like power rules and rewritten it using proper algebra steps into something that is. Now at this point we can take the first derivative, we can take the second derivative, we could take however many derivatives we need. For simplicity's sake, we can maybe write that exponent as a 1, even though it's not really necessary. So f prime of x, that's going to be, well, just 1 times x to the 0, which is just 1, minus 3/2 x to the negative 5/2, minus 2 x to the negative 3. Be careful with the negative exponents that when you're subtracting one, you're doing it properly. The second derivative, now that's just the derivative of a constant, which is 0, plus, well, that's negative 3/2 times negative 5/2, so that's 15 over 4, x to the negative 7/2. Negative 2 times negative 3 is positive 6, x to the negative 4. And so the third derivative is going to be, again, 15 quarters times negative 7/2. That's going to be negative 105/8, x to the negative 9/2, minus 24, x to the negative 5. And there's no reason we need to stop at the third derivative. If the question asked, we could have found the fourth derivative, we would just keep going. So now that we have these power rules and these nice rules, we can just apply the rules every time as opposed to having to go back to the definition, even though the definition is where this all came from. All right, so that's going to be it for this video. In the next video, we'll talk about exponential functions and also talk about some tangent lines and something called the normal line, which is related.